Okay, in this video lesson, we're going to continue our discussion with trigonometry and circular functions. This is the second part. So, here we're going to do a little review. Secant theta we know was the ratio of hypotenuse to adjacent. So if we actually found the secant of 30 degrees, we'd have to find the ratio of the hypotenuse to the adjacent. Because it's 30 degrees, we can use our 30, 60, 90 triangle and the values associated with Schul, 1, 2, radical 3. So I can place those values on the triangle, and now I can identify the secant of 30 degrees. The hypotenuse is 2, and while the adjacent is radical 3. As we simplify, secant 30 degrees, 2 radical 3 over 3. So just a little review. One more review. If I wanted to find cotangent, recognize old school is adjacent over opposite. Specifically, if I wanted to find the cotangent of 45 degrees, again, adjacent over opposite, draw my 45, 45, 90. Again, apply the values of Schul. So my two legs are 1, while my hypotenuse is 2. So the opposite and the adjacent both are 1. So the cotangent of 45 degrees is 1. So with that as a background, we'll transition to larger angles now. Let's consider, we just did the secant of 30, and we saw that this would be this sector of our triangle. Now if we considered the secant of 390, well, 390 has the exact same initial and the exact same terminal side, making those coterminal angles. So I could take this angle here, create my triangle, and put my values 1, 2, radical 3. So we can presume, again, the adjacent, the opposite hypotenuse. Also, I can use the variables x, y, and r if needed. So the secant of 390 degrees, it's reasonable to presume then it's the exact same as the secant of 30, because both 30 and 390 share the exact same initial, terminal, so therefore they share the exact same opposite, adjacent, and hypotenuse. So from this slide, we conclude that coterminal angles share the same trigonometric functions. So with that as something to build upon, we'll consider this situation. It says without the aid of a calculator, we'll find the tangent of 960 degrees. Well, first thing we acknowledged in the previous slide was the tangent of 960 will be the same as the tangent of any one of its coterminal angles. So it'll be reasonable to first find a coterminal angle that falls within the first revolution between 0 and 360. So let's take out 960 and begin to find its coterminal. We'll subtract 360, got 600. 600 is a coterminal. Therefore, tangent of 960 is the exact same as tangent of 600. Continuing, we find 240. 240 is the coterminal angle that falls within the first revolution of our unit circle. So if I found my 240 degrees, that's the region we're referring to. So this point right here happens to be in quadrant 3, negative, negative. So I'll consider the fundamental things first. The fact that the point is in quadrant 3, and we know the signs are negative, negative. So if we look a little closer now, if I created my triangle, we end up with another 30, 60, 90. More specifically, the 60-degree angle would be our reference angle. So I transition my values of Schul. But again, because we're in quadrant 3, the signs will be adjusted accordingly. So the short won't just be 1, because it's on the Cartesian plane, it's the x value, negative 1. Our long won't be just regular or positive radical 3, but negative. Again, because we're in quadrant 3, all of our signs are negative. And of course, the hypotenuse stays 2. So we can begin now to determine the tangent. So if I projected that triangle off to the side, I've got my 3 values. I could identify adjacent, hypotenuse, opposite, which is also the same as my x, y, and r. And now, so therefore the tangent is the ratio of y to x. Our y is negative radical 3, and the x is negative 1. So therefore, tangent of 960 is radical 3. So because the tangent of 60 degrees in this region or in this quadrant would have been radical 3, or at least the exact same values as 960 degrees. So if we look at all of the things we considered the quadrant of theta. Why did I have to consider that? Because that then identified the signs of the numbers we're actually going to be using. So how did we find that? It was simply the coterminal angle that was between 0 and 360. So how did we find the quadrant we were in? Once we found the coterminal angle, wherever that one was, so is the original angle. Next thing we looked at was the reference angle. Because once we determined the angle stopped here, the terminal side stopped here, we created our triangle. There's our reference angle. From there, we just use the values of Schull. So let's look at a situation. Oh no, we'll look at the different steps we did. First thing we did, we found the quadrant. The terminal side was located. And again, we did that by doing coterminal angles. Next thing we did, now we know what quadrant it's in, we considered the signs. Step 3 was, then we looked at the reference angle. And then finally, we use Schull. So we apply whatever values we need in Schull with the corresponding signs. And then the last thing, we just applied the appropriate values for that particular trig function. So let's look at a couple examples. It says find the exact value of cotan 590 without the aid of the calculator. So step 1 was to determine what quadrant it was in by first identifying the coterminal angle. So the coterminal angle that was between 0 and 360 was 210 degrees. 210 degrees just happens to be in quadrant 3. Quadrant 3, the signs are negative, negative. So step 1 was to first find the quadrant, and we did so by first finding its coterminal angle. Now, let's go find the reference angle. Reference angle, 30 degrees. Recalling, the way we found the reference was by taking my 570 and in this case subtracting a bunch of 180s over and over until we got to a value between 0 and 90 degrees inclusive. Step 4, so now we're going to draw our triangle. So my recommendation is take what you have here and now begin to draw a visual. We're going to put 210 degrees in quadrant 3. So we can see there's our 210 degrees. The reference angle, there's the 30 degrees. So there's a 30-degree angle in quadrant 3. As we now apply our values of Schull, 1, 2, radical 3, placing the values on the triangle with the appropriate signs. So the benefit of drawing it on the Cartesian plane, you could see that this is negative and so is that. So when we apply the values, there we go. Now, last step to apply the appropriate ratio. We're doing cotan. So we know x is negative radical 3, y is negative 1, and 2 is r. Step 5, cotangent is x over y. Substitute the values and then simplify. Cotan 570 is radical 3. Got, I think, 2 more examples. Let's see. Now we're in radians. So you apply your understanding of degrees and just do the conversions. So step 1 was to find the coterminal angle. Our coterminal angle just happens to be 3 pi over 4. Again, I simply subtracted 2 over and over until I got to a value between 0 and 2. 3 pi over 4 is in quadrant 2, and of course the signs there are negative positive. Step 3 says find the reference angle. Well, the reference angle with something over 4 is going to be pi over 4. So now let's go ahead and draw what we have. So if I drew a 45-degree angle, or pi over 4, in quadrant 2. There we go. There's our 45-degree angle. And the reason why I converted it to degrees here is because we're about to use Scholl. Scholl is for 45, 45, 90, and 30, 60, 90. So Scholl tells us 1 radical 2. Because I drew it on the Cartesian plane, I can see this is negative 1, while this is positive 1. All right, so our x, y, and r, negative 1, 1, and radical 2. So step 5, cosecant is r over y. R is radical 2. Y is 1. Simplify. So cosecant 19 pi over 4 is radical 2. All right, one last one. This is kind of a special case. So right now, step 1 is to determine where it's located. Here. The deal is that the coterminal angle just happens to be pi over 2, which is on the y-axis. So it's not in quadrants 1 and 2. It's on the y-axis. So this is a special case here. Here's what makes it special. Because it's special, or what makes it special, is the fact that if you are on an axis, something that you know is that if I put this point on the y-axis, I know something about the coordinates. I know that the x-coordinate is 0. Don't quite know what the y is, but I do know the x is 0. What else? If I actually draw a circle here, then I begin to bring in my r. I see that the radius is the exact same as the distance of y. So we end up with something very unique. One of your 3 values is 0, and the other 2 will always be the same. So if I look at tangent here, tangent of theta is y over x. Y is some number. X, we know for certain, is 0. And anything over 0 is undefined. So this what makes this unique. There's no need to do Scholl. Guaranteed, if it's on an axis, one of your variables is 0 and the other 2 are the same. So there we go. If the terminal side of an angle is on the x, or is on an axis, the trigonometric ratios will be one of 4 possible answers. So here we go. Either 0 over some number. So there's the one value is 0. Don't know what the number is. That answer is 0. Or a number over 0, like what we had here, undefined. Or a number over itself, meaning if you was working in this case with the y and the r, we don't know what they are, but we just know they're the same. And the last possibility is if the two numbers were the same, but one of them is negative. Meaning, imagine if this point was down here. The radius would still be positive, but the y would be negative. So this is what I meant, that once you find that the terminal side lands on an axis, it's a wrap. It's going to be one of these 4 responses. So there we go. Hopefully that helps.